respective PDF with the specifications and all. So the content of this presentation include the layout design flow, the need for the design rules, some brief understanding of the stick diagram, lambda-based design rules, and designing of the inverter layout, LVS simulations. So this is the first slide in which the layout design flow is shown. So we can see from here that the first step towards the designing a layout is the functionality and the performance specifications. So once you need you if you are if you're going to design a layout, for that you must have some specifications and some functionality of the circuit, so that after designing a layout you will be able to check whether it is working or correctly or not. So for that, you need some specifications. Then in the next step, you will be having some circuit topology, which you will design in the schematic, and then you will convert it to, you will design it in the layout. And after that, other process will be taking place. So after the circuit topology, while designing the circuit topology, you need to know about the parasitic capacitance. You should estimate the parasitic capacitance at earliest, because if you are able to estimate the parasitic capacitance, then your layout and your schematic will not be that much differ. So for that, you need to estimate the parasitic capacitance. In the fourth step, there will be some initial sizing of the transistors. So now, if you are knowing the parasitic capacitance, somewhat around idea. After that, you will size the transistors in the complete circuit. After sizing, your schematic design will be completed. So after completing the schematic, now you need to go to the layout part. So for that, as Sakri sir has already given the basic understanding of the stick diagram, so you need to lay out a stick diagram for the layout. While while designing a stick diagram, you must be able to know that how your circuit, how your layout will be looking like at the output at the end. So after the stick diagram, there is a mask layout design. So the process we will show in the subsequent slides, how to design a layout. So this step will be cleared after some time. After designing a complete layout, there is an option in the design rule check, for that is for DRC. So there are two kinds of checking. First, we can check at the every step. So we'll lay out a diffusion and we check whether it is correct or not. On the second option is complete design and after the design rule check. So it is preferred that if you check at the every step, so that it will not be accumulated at the end. So after the DRC check, there is a parasitic extraction. The exact parasitic available in in your layout will be extracted, and based on that estimation, that parasitic extraction, you will simulate your circuit. And if your specifications, whatever you have assumed at the first stage, if this matches to your output, then the final layout is completed. If it is not, then you need to redesign or you resize the modify the layout, and then again move to the DRC and other process. So in this way, you will be having the complete layout, designing of the layout. It will be completed. So now going to the next slide. This is the need for the design rule. Why we need a design rule? Why we just cannot place everything in the layout? So there is 2 points: why and why if not. So if you are using the design rules, there will be better reliability. Reliability means if you are after the completion of the layout, when you take it as a tape out after fabrication, it should work. So if you are following the design rules, there are better chances that your tape out will work. If you are not doing that, then there will be some problem in functional or non-functional circuits you can get at the output. And the second is the better area efficiency. So if you use the design rule prescribed by the technology files, then your area can be optimized in a very efficient way. Otherwise, the wastage of area, everything will be is possible. The third is the increased probability of the fabricating a successful product on a wafer. So that is the same thing that I have just not told. If you don't do it, don't follow the design rule, there is a area problem and the functionality may not be achieved at the end. So that is a need for the design rules. So this slide shows the stick diagram. As sir has mentioned that there is multiple layers. So the green shows the inactive, the yellow shows the P active. It can be shown in brown also. So we can see here where and the green and red are crossing. So when the red means poly and this green means the active layer or diffusion. So when there is a cross, it makes a MOSFET. So every time we are getting this poly cross, we will get a MOSFET. So we can see here, this is the poly and this is the diffusion. So we are getting a cross here. So it means it makes it a MOSFET. And here also. So this is the PMOS and this is the NMOS. So in a similar way, there are others, metal 1, metal 2 also is shown here. In this, the last figure, we can see there are two types of two kind of architectures we can use for the inverter design itself. One is this poly is placed in this way, and another is poly is placed in this horizontal way. Here is it is vertical way, and here is horizontal way. So if you use this horizontal way, means crossing is with poly is horizontal, then you may have some extra poly requirement. So if you are using extra poly, there are chances that your signal may not get at the output correctly because it has a high resistance. So your input signal can lost in the poly itself. So it's better to use less poly in the layout. So this is just a basic stick diagram of the layout. After that, we'll now the magic tool. Now we are coming to the magic tool. In the magic tool, this is the lambda based design. So lambda is one parameter which is related to the length and the width of the transistor and the other features. So how it is related, we will see in this slide. As sir has also shown you that the lambda is L is the minimum feature size of the transistor. So lambda will be L by 2. So for better understanding, we can take L, the length of the transistor is equal to 2 lambda. Okay, so length or width of the feature is the 2 lambda, and the minimum separation between the two features is also 2 lambda. Okay, we can see in this figure, the if there are two features or two contacts, there should be 2 times lambda difference. The distance should be 2 times lambda or more than that. That is the minimum value. So based on this lambda design, we can size our layout. For transistors, we can see minimum width is 3 lambda, minimum length is 2 lambda. For poly overhang, this is 2 lambda. So we will see everything in the session, that is that the Puneet will show you that how much is the 2 lambda, how much is the 3 lambda. Everything we will see in the layout session. So here I have mentioned the metal 1, metal 2. So the minimum width and the minimum spacing between two metals, this is the 3 lambda. For metal 2, the minimum spacing is somewhat higher. So these are the design rules which we need to follow while designing the layout. If we don't follow these rules, we will have the DRC errors. Otherwise, our layout will be somewhat complex and we will not be able to understand fully, and output will not be as good as if we follow the design rules. So yeah, this is the first window of the magic tool. When we open the installation part has already been covered in the PDF that has been shared. So most of the people or all of the people must have installed the magic tool. So while we open the magic tool, we will be having this first window, and one more window will be here, that is for the write up section. So this is the main window for the magic tool. In this window, there is not the grid is not on. So if we want to on the grid, so we can write directly G in that console, writing console, or we can write G, or we can type G, or we can write grid. There are two options. We can click on the G button in the keyboard, or we can write grid in that console. So we will get this gridding in the window. So what this grid shows, the width and length of this grid is the lambda, what we have shown here. So that's why it is called the lambda based design. So this the minimum size will be the lambda. So if we want our MOSFET to be 2 lambda, 3 lambda, then we have to just take 2 box or 3 box like that. The sizing will be, we will show you that how to select these things. So the second step is to how to draw PMOS, NWL and poly. So how to select means, if we click on the one corner of the box, and the left click should be at the one corner and the right click should be at the other corner, or the other corner of the different box. So then it will select the complete box from here to here. So multiple box can be selected by clicking left and right uh, sequentially. So in this way, we can select from here to here. Then we will click left click in this corner and right click on this corner, so that we can select the complete this part. So in this way, we can select this. After, if we are able to select, then we need to paint it. The paint is the command that we will use to place an anvil, the P diffusion PDC for the drawing of the PMOS. So suppose there is a poly here. So if we need to place a poly, then we will select these two box. Then this size should be more than minimum or the minimum of the design rule. And after selecting it, we will go to the writing console. We will write it paint anvil or paint poly. So it will paint this as a poly. So in the similar way, we can make anvil, diffusion, and the PDC. PDC is the contact that this black is shown. That is the PDC. The orange yellow is shown. It is the diffusion part. Okay, this complete is the well. In the same way, we can do for the NMOS in the downside. Okay, that I have not shown in this one. We will show in the next. So for if you want to increase the size of the W by 1, size of this PMOS by 1. So what you will do, you will select the complete MOS and you will write in the in the console E, or you will press E, or will write, or you can write stretch up to 1. So it will scratch these things up to 1. It is here this much box. If we write scratch up to 1, then it will increase 1 box like that. So you can increase multiple also by doing the same. In this one, here we have shown for the NMOS. So the similar way we can paint the diffusion, PDC, and the contact. So everything can be done very easily. Uh, if you don't want to select by the mouse, you can write this command box 4x4 in the writing console, and then write paint via. So it is somewhat difficult also, but the selecting the boxes is somewhat easier if we are going to design a bigger layout. So after that, yeah, this is the contact. In this contact is shown. After the steps for the layout, in this metal 2 and the VDD ground line are placed. So metal, in the same way we can select the metal 2 here. We can also select, there is an option by clicking this point, there will be the console will be open here, and there are everything will be given in that box itself, such as poly, diffusion, P diffusion, and diffusion. Everything will be given in this box. You can select from there also, or you can write in the writing console. Okay, so in this way, we will be able to make the complete layout of that inverter. While designing inverter, the important thing is the labeling. Or while designing a layout, labeling is important. So after that, you need to label the VDD, ground, input, output, everything. For that, we use the command label, and then we write in. Suppose our input is in, then we will write in. This we will write in the console after selecting the part, wherever the input is. We will select this box and we will write label in, or label out, label VDD, label ground. Everything will be label. So after that, this will be the final layout of the inverter. So there are two contact for VDD, two contact for ground. One is for input, one is for output. These are the metal contact. So this is also a metal, this is also a metal. So, and this is the poly. So there is a connection of the contact for the poly. Okay, so in this way, this is the complete inverter layout. So what we will do, we will just extract, or we will write extract all. So what it will done, it will extract all the parasitics available in the layout, and then we will extract this file to a spice file. So for that, we will use the extract to spice command in the writing console. So well, when we will doing the extract to spice, and a spice file will be generated. That spice file, after that, we have two options to check the LVS. LVS means the layout versus schematic. So the layout versus schematic, why we do that? We want to check whether the functionality and the operation is correct or not. So we will run the schematic and we will run the layout, and then we will compare both the results. So for that, we can do two things. One thing is using the ngSpice and NetGen that is given in the tutorial PDF that we have shared. The second thing we can do is we can run the same circuit in the schematic in the layout. Then we will generate the spice file from the LT spice, And then what we will do, we will compare those files first in the LT spice, the second in what we got from the layout, the spice file. The difference will be the area occupied will be given in the file which is taken from this layout. Okay, so what we will do, we will run that file in that LT spice, then we can directly check the results whether it is coming correct or not. For comparing two files, we will run both the files directly, means simultaneously, so we can check whether the output is similar or not. So in this way, the layout of the inverter will be completed. So now I will hand over to the Puneet to give you the exact simulation environment, so that you can easily understand how to lay out the layout. Okay. So these are the references what you can use. Video is also there to understand better.
Thank you, Mike. So I share my screen. So we already provide the installation of Magic or the WL Ubuntu distribution for the Windows, and if you have the Linux, you can easily install the Magic in the Linux. So I just start the Ubuntu, and we also share that how you can add the technology files in the Magic. So I just launch Magic. It's the command Magic. Yes. It's Magic slash T SCN6M underscore deep dot 9. So okay, this is the toolbar. In one, we can draw the layout, and the second, this is the TCL console. Then we can write our comments in this. So first, we check. We are using the technology tech manager. So we are using TSMC 0.18 micrometer technology file. So the lambda is given is 0.09. So I just press G here. So it is a box. So a single box has the lambda value is 0.09. So if I click two boxes, the left click for to select the box and the right click to resize the box according to. So if I select this box, its value is 0.9. And if I want it's to 0.18 micrometer, so I have to select two boxes. And now there is an option, that toolbar. All the layers in that toolbar is given, that NVEL, P diffusion, N diffusion, metal 1, I think metal 2, contacts, PD contacts, and substrate and all. So first we design a circuit. So first we design a circuit in LT space. So this is our inverter circuit. So we choose the values. This is 0.72 and this is 0.18. So this is a minimum length in 180 nanometer technology, and this is I think four times of that. And for NMOS, I am taking the two times of half of the NMOS width. Okay, and just I simulate and apply the pulse and I simulate this circuit. So this is my input and output. Okay, because at last we have to do the LVS LVS comparison. So that's why. So we have to see the netlist. We have to generate the netlist from the LT space. So this is the netlist that we can use to compare both the layout and the schematic. So we can generate this netlist. I'll save it as inverter. This is the netlist I have saved already. Now, so here the uh, first I have to create a P diffusion. For P diffusion, the W is 4 times. So for 4 times, the 4 into because the lambda is 0.09, so it's 8 lambda. So the value of lambda is 8. So I have to select 8 boxes. So this is a my W. So I have to select. If I see here, and if I go up from here to here, I can see this tumbler. I can 0 point. So this is 0.72. So these are the 8 boxes, and you can also see from here to here. If you go upward, you can see there is 0. Here this is 0.72 microns. So the minimum size is 4 lambda, 4 lambda, and 4 lambda. So I have to select the 12 boxes. Okay, and now just right paint. So this layer will form. Or if you want, if you have this middle mouse, you can click on this the P diffusion. So by that way, you can also uh, plot this layer. Okay, and to delete this layer, you just select this whole layer and click A, and just press delete. Now the length of my PMOS is minimum, matlab 2 lambdas. So I have to select 2 lambdas here in between. So this is the 2 lambdas. Okay. So if I just click polysilicon, and you can see there is a white dotted. So this means, and you can see here there are 2 DRCs here. So to resolve that, I have to, because this is the minimum size of poly that we can use for design. Okay, now this is the PMOS is created here. This is the source, and this is the drain. Now I have to create the NMOS. So NMOS is the half of PMOS. I just select the 4 boxes, and I just now I can write the command, or I can just click the middle mouse, and I just get that layer. But this is a DRC error that so I have to move this because this is not the minimum length. So I just select that box, press A, and move it down while pressing the number lock 2, 4, 6, and 8. So now there is no DRC. Okay, the same thing, I have to draw a poly here. Okay, so my NMOS and PMOS is completed. Okay. Now I have to connect this that drain of PMOS and NMOS together. So I'm using a metal, and from this to this, I'm using a metal one, and I have to place a contact for P diffusion to metal on contact. So there is a ND contact. So I place a ND contact, but it's so error because the minimum value for ND contact is 4 lambdas. So we have to use 4 lambdas here. Now this the same thing. I just place a metal, and for PMOS we have the PD contact. Now I have to place a, because in Magic this is a P substrate. So for PMOS we have we have to develop an well. So for developing an well, there is a option that n well. Just click on it. Click on that. You have to create an well. So, but there DR series, so you have to solve that. So, okay, make n well much bigger. Okay. Now for that VDD and power supply, as told that the all VDDs at the top corners and all ground at the bottom corners. So we have to make a VDD. And for body connection, because there is a body always connected to, for PMOS, the body is connected to the higher potential, and for NMOS, the body is connected to the lower potential. So for to connect that body, we have to provide a contact. So this contact automatically connect this body terminals. So 1, 2, 3, 4. So 4. So for PMOS, we have to use N substrate contact. Let's place N substrate contact. Okay. To increase the, what is the 4 by 4? Increase the angle also. So just try to move that part about. For this, let's select one. Move it. Just 4 and 4. This is why. Okay, we have to for copy command. I have to place 2 or 3 contact. So for copying this same, so we just select this terminal, press A, and where we want to copy, just put the cursor there and press C. The same thing we have to. For ground, so we have to provide P sub contact. P sub contact. I am selecting again and just provide 3 contacts here. Okay, and this is the source of NMOS and this is the drain of NMOS. The source of NMOS is connected to the ground terminal. So I have to connect the source to the ground. Okay, and I just place a PD contact here. So ND contact here. And this PMOS is the source of PMOS is connected with the VD. It's connected. Just place a VD contact. So the this is the for zoom in. You just press Z, and from zoom out, you just press Shift Z. So this is the layout of inverter, and now this is the input. This is the output. So we cannot directly give the input to the poly. So we have to take a metal connections. So for taking out the metal connection, we connect a poly poly contact, and from poly contact, we can take out a metal connection. Okay. Now we can give the input here and output here. So providing the label input and output, we just click the press the left click, and on that instant, on that point, we all press the right click. So there is a this will be created. So we just press it here, and we just in the command console we just type a label VDD. Because VDD and ground is the global nets, so we provide X20 marks. Here VDD. Now we also provide the ground. Now we have to label the input. So for input, because this is all is the input, we can just label it. Label input. Take output from here. Now our that whole inverter is completed. The layout of whole inverter is completed. So we have to extract this inverter. So for that, we must save that inverter. Save my inverter, and we have to extract all the parameters, all the parasitic. For that, we have to use extract command. Extract all. Now this file is created. That is myinverter.ext. But we have the spice simulation, so we cannot directly run the ext file. So we have to convert this ext file to the spice file. So to convert, we have the command ext to spice. Okay, now we got the file ext to spice. Now I just write this. Go to the Ubuntu. Just say exe. So this is all the files is created, that myinverter.exe, myinverter, and the spice file of myinverter. Okay. You can directly click here and see it. And if you want to see from the console, you can just type vim myinverter.spice. So the file that is created, that is extracted from the layout. Now we have to simulate this layout. So for that, what? So we have to install ngSpice, and we have to create a spice file. Okay. For I'm also for I just create a spice file .sp. Now I just first we have to include technology in which we we want to simulate that file. So I am using TSMC 180 nanometer dot lib. And we have to include that file also. This is my converter display. We are providing the all the connection that V1 is from VDD ground 1.8 V2. We have to give the input of pulse input to ground pulse 0 to 1.8. Delay time 0, rise time we can give 0.1 p per second, hold time 0.1 p per second, and the T on time is 0. If I am applying the 1 nano ampere pulse, the hold time is the on time is T by 2 minus rise time or hold time, and 1 time. I'm using constant analysis. Start from 0.1 nanosecond. So you can also see that file from here. But we can also create that file. That like that. If you design, you can create this file. Okay, you can copy paste this file again and again. That if you want to use that file, just copy and paste it. This file I created. Also, we are using the same labels: VDD ground, input ground, pulse. Now I have to check the simulation. For that, we use the NG space. Later, NG space. My this runs the files, and I just comment to run all the files, and all the voltage potential is already calculated. Now I have to plot input and output. So just plot input and output. This is the this red one is our input, and the that blue one is our output. So we have to compare this to the that LT spice. So what we have to done, we just uh, the spice file that we created. We just copy this data from here and this file that we already created. We can paste that data, or we can just use that value, because only these values are different. So we can directly write this value here and we can simulate that, or we can just copy and create a netlist according to this file, and we can save that file into .cir. I already done that before, so I just create that CIR file, and we only just have to click on it. So it will directly open in the, but it's take time because you are using TSMC, so it's take too much time. If you don't use this technology files, it will simulate easily. If I just delete this comment, okay, this is an sequence. First, here we give n mouse and mouse, or we can change here also. We can plot this. And but for including a TSMC, it's take a little more time in LT space. So we can use a second software that NetGen, or there are some more software that can we can use for the that LVS comparison.
Okay, then now I will explain the work that you need to perform in this lab session. So, can you please stop sharing? I will share the screen. Yeah, thank you. So, I think this PDF you must have got or you will get in some time. In this experiment, you need to design a layout of a single stage differential amplifier. So in which we have given you a specification to check at the end while you complete the layout. So these are the specification to be matched. That is phase margin, loop gain, and other. In this single stage amplifier, we are having this current mirroring and this input stage and the load stage that we have already seen in the previous lectures. So the the values for this aspect ratios are given in this table. So based on that, you need to design the layout of this single stage amplifier. So we have told you we have shown you that to how to design a layout. Now uh, we have shown you for two MOSes. So now there are 4, 5, 6, 7 MOSes. You need to complete it. And if there is any query related to the layout designing, we are available here. So we can discuss right from here. So there are some videos also, the references we have given to how to design. Suppose if you are having some other problem, so you can also see these videos. So yeah,
So I request the participants to please try these layouts which Puneet and Mayank have just given us, and let us know if you are facing any difficulties.